Hi everybody, this is Dr. Bricker here with a video for Emission Spectrum PNW Lab. Let's take a look at it. So it's a little bit shorter than some of the other labs. We're going to take a look at hydrogen's emission spectrum and then try to come up with, try to figure out the emission spectrum of some unknown elements. Actually, we'll be given the emission spectrum. We can match them up with some known wavelengths. Okay, so first part here, spectroscopy. Study of how light interacts with matter, and we've talked a lot about hydrogen. So the emission spectrum, the idea is an electron is in an excited state, it drops down to a lower energy level and emits a photon, and we're going to be able to see that today, and we're going to do some calculations today. So here's a formula given in the lab. This is used to calculate the wavelength. 1 over the wavelength is equal to RH, this new constant we haven't seen before. For hydrogen, it turns out to be 1.0974 times 10 to the 7th per meters, and then times this quantity, 1 over n1 squared minus 1 over n2 squared. So n1 is the energy level that you end up at, n2 is the energy level that you started with. So the notation's a little bit different than the book. In the book we went from n to m. Here we're going from n2 down to n1. It doesn't mean that the energy level is 1 or 2 or 3. It just means the one that you're starting at is called N2, and the one that you're ending up at is called N1. So let's see what we can do with this formula to make things a little less complicated. This formula is good, though. You can use this to calculate the wavelength of the photon that's emitted. We haven't seen this formula yet. Let's see where it actually comes from and maybe see a more usable way of that. Okay, so again, we're going from N2 down to N1 and emitting a photon. So for hydrogen, we have energy level is minus 13.6 eV divided by N squared. So this would be the energy of the higher energy level. This would be the energy of the lower level. So we can take a look at the difference in energy. So energy of the higher one minus energy of the lower one. And then actually put this and this into the formula, and we get this thing. You can take the negative sign and distribute it through this formula. So then it becomes 13.6 EV 1 over N1 squared minus 1 over N2 squared. Note, this was N2 minus N1, each of those squared, but the minus sign was out here, so I've distributed the minus sign through, and we have that. What we've been working on recently, difference in energy, is HC divided by the wavelength, and we've used our nice HC as 1240 EV nanometers divided by the wavelength. So if the difference in energy is this quantity and the difference in energy is this quantity, those have to be equal to each other. So in this next step I've set those equal to each other. So 1240 EV nanometers divided by the wavelength is equal to 13.6 EV and then times this quantity here. So let me solve for 1 over the wavelength. So 1 over the wavelength, I basically just divide both sides by 1240 EV nanometers, and I end up with this. This looks just like the constant that you saw. This is per nanometer, though, instead of per meter. So this is where that formula comes from that you just saw. Now in the lab, you're going to have to calculate the wavelength, so let's go ahead and do that now, and hopefully that'll make your life a little bit easier. So 1 over the wavelength was this quantity. Now I want to calculate the wavelength, so let's just invert both equations. Take the reciprocal of each side, in other words. So 1 over the wavelength becomes the wavelength. Nanometers goes to the top. 1.0974 to the minus 2 goes to the bottom. So I've literally just flipped those around. And now I've got the inverse of this quantity. So take this quantity, take the inverse of it. In other words, 1 divided by that. Actually, you do the math here. This would be like 1 over 1.0974 to the minus 2. When you actually do that, you get 91.1 nanometers 1 over N1 squared minus 1 over N2 squared. And you've seen this formula before. That's really where it's coming from. And that's the useful way of doing it. So remember, you're going from 2 to 1. But when you actually put the numbers in, you'll see that the denominator down here is positive then. Okay, so that's going from, again, N2 down to N1. So N2 is bigger than N1. Okay, so use this formula to calculate the wavelength. let's take a look at this. So although you can use this if you want to, that would work out fine. You can do that. These answers are in nanometers, so you should just use the one that we just came up with. The wavelength being 91.1 nanometers divided by 1 over n1 squared minus 1 over n2 squared. Okay, so in this first part of the lab, you're just doing some calculations. So here you're going from n2 is equal to 3 down to n1 is equal to 1. Put the numbers in and get the number here. Figure out the wavelength. And the answers are in nanometers. The equation that we came up with was also in nanometers, so that's nice. This is not visible light here, right? That's not in the visible spectrum. This is the so-called Lyman series. Okay, and then we're going from 2 down to 1, so same thing, put the numbers in, see what you get. Third one here, looking at the values you found in the past 2 questions, will you ever see visible light? So visible light is 400 to 700, or either 1 or 2 in that range, and don't be surprised when you get what you get. And then we're moving into the visible part of the spectrum, when you go from like 3 down to 2. So actually do the calculation. You've actually seen these numbers before from class. We looked at the hydrogen spectrum. So do that calculation. Same thing from 4 down to 2, and then from 5 down to 2. Okay, so you do the calculations, and then you could actually watch this video. Let's take a look at it here. So this is the tool that we'll have. Whoops. And in just a minute, this is a hydrogen light source, and it's going to be the light's going to be going through a diffraction grating. It's going to split off, and we're going to see some bright spots. Okay, there, that looks good. They turned the light off. So we have 3 lines. It looks like there's a whole bunch of lines. We want to focus on the 3 brightest ones. So there's a line here, there's a line here, and then there's a line here. So make sure you write those down. These are in nanometers, and it's getting increasingly bigger as you go this way. So 400, 425, it's 450 here. So, figure out what this one corresponds to, what this one corresponds to, and what this one corresponds to. Okay, let's go back to the video, or let's go back to the lab. So, write those down on a piece of paper because you're going to need them in a minute, as it says here. So you have to lock answers and continue. This is my fake persona Testerson doing this. Okay, so you've written those down from the previous one, and here, what are the three wavelengths that you measured? So the ones that you just wrote down. What are the 3? Do these match the values you found in your calculations? So you did the calculations above. Are they the same? Probably when you measured, there's a little bit of looking at it and judging where the line actually is. So don't be surprised if they're off by a little bit, but they shouldn't be off by too much. Okay, and this is kind of a fun part here. You could load up these different videos. Here's gas 1, for example. We'll put the tool on here. And we want to figure out what gas 1's actually made out of. Okay, lights out. So you see all these different emission values, these wavelengths. So, you can write those down, go back up to this table, and try to figure out which one that actually is. And then the same thing, put in gas 2, do the same thing, write the gas 2 lines down. Let's just do one more. Gas 2, load. Make it bigger. You can, let's put the tool out here, and we'll play it. Okay, so same thing, write those down, then you can compare it to the known values to see which one this actually is. Okay, so a little bit of detective work for you there. Same thing, this is, okay, so what's the gas in video 1, what's the gas in 2, what's the gas in 3, what's the gas in 4. Okay, so you can, do your detective work, figure that out. And now this last one, another important fact of gas spectroscopy is that gases, Gases emission and absorption spectrum are the same. Just remember, in the absorption spectrum, you won't see all of the same lines as in the emission spectrum. The reason being, a gas is rarely above the ground state, so you're not going to see the missing lines for levels above the ground level. So those you don't generally see. Most of the time, electrons are in the lower energy level, so you're only going to see the missing ones when you transition from ground state to a higher level. Okay, so if you measure this absorption spectrum, you measure this from a nearby star, and here's some absorption spectrums for hydrogen, helium, sodium, and lithium, and we want to know what elements are present here. So I'll give you a hint. There's 2 of them. So take a look at hydrogen, see if it matches up. Helium, does it match up? Sodium, does it match up? And lithium. So from that, put those 2 together, figure out what the actual absorption spectrum of this star, what it's actually composed of. Okay, so again, there'll be 2 answers there. All right, if you have any questions, just email me and I'll talk to you soon. Bye-bye.